homework last night was this. I want to go through that with you. Check your answers, check your work, make sure that it looks right. I'm hoping that you might have gone out and kind of checked your work along the way with this. Because I talked to you the other day about being able to go out and Google image any of these. So you can do that, and then you can check your answers to these structures and that sort of thing. Get your homework done, you guys? Any questions on 1, 2, 3, or 4? Anything that doesn't make sense to you? Yeah, I just didn't draw them in. So you'll start to learn with these that the ones that we really care about are around the central atom, and we're going to talk about that today and why as we get into kind of lecture. And so I get a little lazy with some of these sometimes, and that's what I did there. All right, let's go down to 5 and 6. Let's see if I can squeeze. I don't know that I can squeeze 7 and 8 on there, all of it anyway. Gonna move that out of the way. It doesn't help enough. Okay. Yeah. Here's the rest of 7. Any questions on 7 or 8? The more you practice these, the easier they get. All right, let's move down to 9 and 10. Now 9, depending on how you drew it, you could draw 9 technically this way. But the problem with that is that that's going to put your negative formal charge on the carbon. And so that's why this structure doesn't work and this one does. So that's why I wanted to try to like show you guys a couple of times. This is a real good one to kind of show you where, yeah, you could draw this differently, but this drawing isn't acceptable because that formal charge, the negative values on the less electronegative element. Okay. Then we had ozone. We had talked about that. We talked about resonance yesterday, how you can draw resonance here. And then another way that you can show resonance is by using a dotted line in place of that double bond. Then you had to look at Lewis structure for phosphate. So this is the way it was drawn. And with this, you've got a negative charge on the less electronegative element. You know it's the less electronegative for a couple of reasons. First of all, it's listed first in the formula. Second of all, it is the central atom, which tends to be the less electronegative of the atoms. So therefore, we wouldn't want to draw it this way. If you redraw it like this, then that's going to change that negative formal charge to its right location. All right, come on. There we go. And then down here, which structure would be the best? A, B, C, or D? be because there's no formal charge on any element when it's drawn in this fashion. Okay, questions? All right. So what we're going to do today is we're going to turn our attention over to something called Vesper Structures. And I like the notes. I redid the notes, so sorry about that. All right, so Vesper structures are a way of showing you how to draw these atoms or these molecules properly based on the actual shape that they take. And what Vesper stands for is valence shell electron pair repulsion. So when we have these, what happens is your electrons, because they're like charges, are going to repel other electrons nearby. And they end up giving a distinct shape to your molecule. And you can predict what those shapes are and know what the bond angle to the central atom is. So non-bonding pairs or lone pairs are going to repel more strongly because they're actually attached directly to that central atom. So they're going to have more of a push or repulsion on the other ones, on the atoms that are attached to it. Okay. So first of all, you're going to draw the Lewis structure. You're going to count the electron pairs and the bonding atoms around the central atom. So the central atom is the one that we really care about. And then you're going to use a chart that I'm going to show you how to use in a few minutes to be able to predict the shape for these. Okay. So here's one chart you can go with. I like a different chart better though. And this is the one that was in your original packet. So you should be able to locate this and have that sitting out on your desk next to your notes. So take a second to do that real quick. Okay, so anybody not able to find this sheet in your packet? All right, so this is what we're going to be working with to be able to figure out these shapes. So the first thing you do is the Lewis structure. So you should be able to do the Lewis structure for water now. So you've got your oxygen, you've got your hydrogen here, and you've got two lone pairs of electrons on your oxygen. So draw that shape, and then I'll show you how to figure out in the chart what it actually looks like. So when you draw this, how many atoms are bonded to this central atom? How many atoms are bonded to the central atom? 2. How many lone pairs of electrons do we have? 2. So then you go over to this chart. You're going to find how many are bonded to it, which you said were 2. And then you're going to find how many lone pairs you had, which you said is 2. So you go down here until you find where it says 2, 2. And then I got rid of this column on your chart because you don't need it. You need to know this one, which is bent or V-shaped, and you need to know the angle. So bent and 104.5 is what your answer would be for this one. So its shape is bent, and the bond angle to this central atom is 104.5. Okay, and what that ends up looking like, I'm going to blow up another balloon for this. So I use balloons to kind of demonstrate what these things end up looking like. And the lone pairs of electrons have more repulsion. Make myself dizzy this time. Look at me get balloon animals here. Every time I do this. Now I'm not staticky. All right, so this is what that ends up looking like in kind of a three-dimensional structure. It's not. We're okay. We're good. I'm done squeaking for a minute. Sorry. So this is what that looks like. So you've got, these are your 2 bonding atoms here, and these are your 2 lone pairs of electrons. So these lone pairs of electrons then have more of a force, and they're going to push it down. So when you draw it on the board here, it looks like it's in one straight line. But in reality, what's happening is these 2 atoms are getting pushed down. Okay, so they're getting pushed down out of the way. Okay, so carbon dioxide then, carbon is here. It gets double bonded to your oxygens. So this is what its Lewis dot structure looks like. So I'll give you a second to write that down. So this one, our central atom has how many bonding atoms? 2. Are there any lone pairs attached? So in your chart, you're going to find 2 and 0. So 2, 0, it says that it's linear, and its bond angle is 180. So linear and 180. Okay, here's the Lewis structure for the next one. See if you can check your chart and figure out what its geometry would be. Okay, so you should have seen that there were 3 atoms attached to the central atom. So this is 3. And are there any lone pairs? So what is the shape here? Trigonal planar. And its bond angle is 120 degrees. Okay. So see if you can draw some of these and figure out their structures. Take a minute to do that. You probably want to go back and listen to the video. So I can draw like these in for you, and you can at least be able to do this part of it if you'd like. I always have to think about. Okay, here you go. All right, did you get the first one drawn in? This is nitrogen. I'm going to have my fluorine here. I'm going to have my 2 lone pairs of electrons. Okay, so you should have seen that this one is the same as the, no, this one is not. It's 3 and 2, which is Trigonal Pyramidal. I think it's 1075. Trigonal Pyramidal, yep, 1075. Here's my carbon. I have my hydrogens attached. So this one ends up being tetrahedral. And it is 109.5. And I'll show you what that looks like here. Oh, there it is. I got that one good and attached. He's not coming apart. Oh, why did that come out? That's weird. Yeah. Oh, that doesn't work. I don't get broken. Walmart balloon. I don't have any more orange. This is the last orange. Must have had a bad lot. Come through. Let's use red then. Nope, that one's cut too. Good grief. Somebody just go through here and cut my balloons with scissors or something? All right. So this is what your trigonal planar could look like. They're all in the same plane. That's where they get that term. Now, the tetrahedral, okay? The tetrahedral, you think from looking at this structure that it's going to be 90 degrees, right? From the geometry of it. But in reality, it's not, because we're taking a two-dimensional drawing and applying it to a three-dimensional item. Okay? So it's pushing down on this. So that's where they get the tetrahedral from. Okay? All right. So the next one is NH4. When you draw that, you've got your H's around here. This is a +1 charge, should have a positive out here. And this is going to have the same geometry as the previous one. So nitrogen then is going to have an oxygen bonded to it. And it's going to have a lone pair of electrons there. Did I put the brackets around this when I drew it for you? Okay. I couldn't remember if I did it for this one or not. All right. So here you have two things attached and one lone pair. So what is the structure here? Right. So if you go over to here, to your chart, we have two things attached and one lone pair. So 2, 1, it's going to be bent and slightly less than 120 is the angle. So bent and slightly less than 120. And then the last one, we have sulfur and oxygen bonded together like this. And it's going to have the same structure as the previous one. Okay, so you see how to use the chart now combined with what you learned yesterday? All right, so your homework tonight is in the packet. It must be 8.5. Now it asks you for orbital type on there. We haven't gotten to that yet. So don't do that on each one of those parts of the packet. Ignore that section. Okay? I'll give you a little bit of time to do that. And then I'll give you some, I've got my caramels and my fudge up here. I'm going to give you a sample of each of those too. Okay?